Hello. More factoring trinomials, nothing new really. These are just a few that are kind of in a special class, so they get their own name and you just kind of have to recognize them when you see them. So here's the first one. X plus 3 squared, remember, is not x squared plus 3 squared. It's x plus 3 times x plus 3. So when you FOIL that out, and we've seen this before, you actually get x squared plus 6x plus 9. Okay, and that has its own name. It's called a perfect square trinomial. You can probably see why, because it's the square of a little linear binomial like this. So here's the other kind, and then we'll discuss them more in general. So it's just these two kinds. Something like if you have the product of x plus 4 times x minus 4, we've seen one like this too. So when you FOIL that out with those two things out, the middle terms cancel. The outer term is minus 4x and the inner term is 4x. So they go away. So that one's easy to spot because in the resulting product, the middle term is just gone. So you have x squared minus 4 squared, basically, right? So that's called the difference of two squares. And just look at x squared minus 16 and think, oh, why is it? Well, it's literally a square minus a square, so a difference of two squares. Okay, so there you go. All right, so I don't want you to think of this as a formula you have to memorize, because it's not. I just want you to see the pattern and recognize that every time you see one of these things, the same kind of thing is going to happen. So if you have something of the form a plus b squared, or a plus b times a plus b, it's going to turn into this. It just foils to that. It's a squared plus 2ab plus b squared. So look at this, right? It's like that. This is x squared plus 2 times 3 times x, because there's two of them always, and then plus 3 squared. And then if you have a minus b squared, so if it was like x minus 3 squared instead, it would be kind of the same, just the middle term would be minus a 6x. And then the last term is still positive because you're squaring a negative number. So then it'd be a squared minus 2ab plus b squared. So all I really want is for when you see one of these, you think maybe, oh, I recognize that. That looks like one of these kind. That looks like one of these perfect square kind. So example. So you could just dive in and start trying to factor that. There'd be a couple different ways to do it. I mean, 49 is 7 times 7, or it's 1 times 49. So you could try it that way. You could do it the grouping way, and it would work out fine. But it's even better to say, hey, look, this first term is a perfect square, right? So 7 squared is 49, and x squared is x. And then this last term is also a perfect square. So that's something to look for. If the first and last coefficients, a and c, are both perfect squares, so be able to recognize those kinds of numbers, right? 16, 25, 36, 49, 64. And the last term is, it may be a perfect square trinomial. It may not be, but in this case, obviously it is. So now you just look at it and say, okay, if it were a perfect square trinomial, so this is 7 squared and this is 2 squared. And so this middle term then should be 2 times 7 times 2. Is it? Yeah, actually it is. Okay, so then you know, and you don't really have to do any work to factor it. You know what it has to be. Okay, so always look at, I shouldn't really say terms, I should say coefficients, but actually that's still kind of right because x squared is a perfect square. Okay, and note that in our factorization, if we take these, the square roots of this, it's 7x, and then this one gives you 2, the number you have to square to get it. So if that were the case, then we have to have that the middle term, so this is the only other thing you have to verify, is the middle term minus 2 times a times b? Yeah, 2 times 7x times 2 is 28x, right? Minus 28x in this case. So don't confuse the capital A and B with lowercase a and b that we use for coefficients. Which all that is to say, like, you don't have to identify what A is and what B is, or remember any formulas or anything. You just have to, I just want you to recognize the stuff when you see it, because it is a special case. And then just agree that this works. So if you were to FOIL this out, you'd have 49x squared minus a 14x minus another 14x, which is where this negative 28x came from, and then plus 4, right? Because it's negative 2 times negative 2. Now, I like to write it more concisely as 7x minus 2 squared. If you didn't do that, I wouldn't mark it wrong. But just since we're learning it, I mean, I think concise is good in math, so I guess I would say, to me, it's nice to leave the answer as 7x minus 2 squared. For a difference of two squares, like this, it only has one form it can possibly take. unlike the last one. So it's always going to be something squared minus something else squared. So these are much easier to recognize because they're the only kind of trinomials, I guess, that only have two terms in them. So they're really not trinomials. So let's look at this. So the thing to recognize is, okay, there's no middle term, right? That should jump right out at you. And then you think, okay, is 16x squared the square of something? Yes. Is 81y squared the square of something? Yes. So if that's the case, and again, I'm talking about square roots, even though we haven't got that in the class yet, but if you know what that is, fine. The square root of 16x squared is 4x, and the square root of 81y squared is 9y. So this has to be one of these. It has to factor into 4x plus 9y times 4x minus 9y. Okay, so just something to look for when you see these. Well, again, I don't need you to identify your A and your B. I just want you to see the format. There it is. And then FOIL that out, right? You get 16x squared plus 36y minus 36, no, I'm sorry, plus 36xy minus 36xy, which, hey, it didn't matter what it was because they went away. And then minus 81y squared, okay? So that's a difference of two squares. I'll touch on this later, but if you ever see a squared plus b squared, it looks a lot like this, and you might think, oh, shouldn't I be able to factor that? No, you can't. That's why I didn't bring it in here. There's no such thing as like a sum of two squares, factorable kind of thing. So we'll see one in a little bit. Oh, we'll see it right now. Okay, so we're getting a little trickier. So this is a fourth degree polynomial, right? Just because it only has two terms, that doesn't matter. It just matters the highest power. So when you look at it, it's like, okay, you think, actually, so 1 actually is a perfect square, technically, because 1 is 1 squared. X to the fourth is also the square of something. What's it the square of? It's actually the square root of x squared. Let me make that clear. X to the fourth is the square of something, because x to the fourth is x squared squared, right? Because you multiply those exponents. So now think about it. Any even power, if it was x to the sixth or x to the 18th or whatever, would be the square of some lower power. Okay, and then 1 also is. Technically, 1 is 1 squared. So this is a difference of 2 squared. So if the first term is x squared and the next term is 1, this would break down to x squared plus 1 times x squared minus 1. It's a lot easier to do it backwards. If you don't believe me, just FOIL this out. You'll see it right away. X squared times x squared is x to the fourth, and then it's plus x squared minus x squared, see you later, and then it's minus 1, right? So it works. So it can be a higher power than just squared, and we can still factor it, okay? So we're actually not done. Implied when we say factor is that I want you to factor it completely. So look at this first term. It is also a difference of 2 squared. So sometimes we factor and then we can actually keep going. So this is maybe more obvious. This is x squared is obviously x squared. And then again, minus 1 is 1 squared. So this does basically the same exact thing. This factors to x plus 1 times x minus 1. It's actually a lot like that, right? Just with 1 instead of 16. Ignore that. Okay, so x squared minus 1 is x plus 1 times x minus 1. Again, FOIL it out. You'll see it right away. So we can go one step further with that. That's the complete factorization. Here I'm going to make it perfectly clear. You look at x squared plus 1 and you think, wow, that's pretty simple. It sure seems like there should be a way to factor that, doesn't there? And yeah, I suppose it does seem that way, but there isn't. There's no such thing as like a factoring formula for the sum of 2 squares. Unless you know about imaginary numbers. I'm actually lying, but you don't. So don't worry about it. Or maybe you do. I don't know what you know. Okay, so just keep that in mind. It's really easy to say, wouldn't that factor to like x plus 1 times x plus 1 or some permutation of that? Nope, it doesn't. You can try, but there's no basic way to factor something like that, even though it looks very similar. Okay, so just use caution. For these, I'm just showing them to you in case they pop up in the book, and I'm sure there's a couple on the homework. So a sum or difference of 2 cubes is a thing, and it'll come up like later in math too. So I don't want you to memorize these formulas, and frankly, I'm not going to put this on the exam. I just would have felt bad if I didn't bring it up. So if you want to tune this out, go ahead. Just it is on the homework. So just here's the formulas. You don't have to memorize these. I don't even know if I have them memorized. Okay. So there they are. So just write that down. If you ever see something that's like a cubed plus b cubed, it factors a plus b times a squared minus ab plus b squared. And if you see something that looks like a difference of 2 cubes, okay, so this is a sum, this is a difference of 2 cubes, that's going to factor to a minus b times a squared plus ab plus b squared. It might be instructive to actually multiply one of these all out and just see, oh yeah, it actually does simplify to that. Because these ones, it's like, it doesn't quite look right. Like, really, that factors to that? Yeah, it does. Okay, so I'm just going to hit you with one example. And because it's not as obvious, like you're used to seeing a number like 9 or 25 and saying, oh, that's a perfect square. But for 8, you're not as used to seeing, oh, that's a perfect cube. It is. 8 is a perfect cube, as is 27, 64, 125, and then who would know beyond that? Okay, so 8 is 2 cubed. 8 is 2 times 2 times 2. X cubed is obviously a perfect cube. 1 is actually also a perfect cube, just like it was also a perfect square. -1 is itself cubed. Okay, so that's a difference of 2 squares. Assume you'd have this formula in front of you if you had to use it. So you just say, okay, if our a is 2x, right, and b is 1, then that's how this factors. Okay, so just saying that those are both perfect cubes. So this factors to that. If our a is 2x and our b is 1, it's going to be 2x minus 1 times parentheses 2x squared plus a times b, which is 2x times 1, plus b squared, which is just 1 squared. And obviously, I'm going to simplify a little bit there. And then that simplifies to 2x minus 1 times 4x squared plus 2x plus 1. So I'm just going to ask you, please multiply this out to verify that it works. You'll see that a bunch of stuff cancels out and goes away, and all you are left with is 8x cubed minus 1. You could prove the formulas in general or whatever, or you could just take our word for it. But it is instructive to see how it multiplies out, because then you see why the formula works, not just here's a formula that works, moving on. Okay, so that's it. That's all I'm going to do with perfect cube stuff. Okay, let's try a couple more. Well, that's just this one. So you look at 48, a squared minus 27b squared. Okay, well, a squared and b squared are obviously perfect squares, but 48 isn't, and actually neither is 27. So you might look at this and just say, well, he said like the only way for there to be only 2 terms is if it's a difference of perfect squares, but these numbers aren't perfect squares, so this must not be factorable. And lots of things are not factorable, right? You'll see that. You just say, oh, you can't factor, it's prime. But you're all ahead of me, and you know, you're looking at this and you're saying, wait, what's the first thing I'm always supposed to do when I see something like this and I'm trying to factor it? Oh, I'm supposed to take out a GCF if there is one. So is there a common factor between 48 and 27? Yeah, actually there is. They both have a factor at 3. So always be on the lookout for that. If you didn't see that, then you'd just say this can't be factored, and you'd be wrong, because it can be. Okay, so pull that 3 out. You're left over with, okay, 48 over 3 is 16, 27 over 3 is 9. Now you say, aha, there are some perfect squares in there, because 16 and 9 are both perfect squares. So this is a difference of 2 squares, actually. It just had a 3 in it as well. So you have to keep the 3, and then just say, okay, what do you have to square to get 16a? You have to square 4a. That's 16a squared. And what do you have to square to get 9b squared? You have to square 3b to get that. So this is going to be 3 times 4a plus 3b times 4a minus 3b. Right? Isn't that beautiful? Okay. So don't ever forget about that. That's something that you have to know no matter what. If there's a greatest common factor, you should always take it out first. And then the next section is 6.5 that just has a summary of all of this stuff in like a general strategy. So I'm not really going to make a video for that. I'm just going to ask you to read it out of the book and refer to it. So as you go through the homework and do these problems, I'm just going to say read section 6.5. Just read over it. You don't have to work through every single problem in it, but it certainly couldn't hurt, okay? Because that's really it. That's all we're going to do with factoring, and now we get to actually use it to solve equations, okay? Thank you.